Hello, everyone, and welcome to this Surface Ventures Mini-Symposium on the effect of electrification on brake applications. It's great to see that some of you are already saying hello in the chat. For those of you that haven't, please do say hi and tell us where you're coming from. It's always great to see where our audience are joining us from for these events. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures, and we're a non-for-profit organization, and our mission is to provide world-class surface and materials science education for academia and industry. We'll be having 4 speakers today on the topic of electrification and brakes. Just to give you some information on that, we'll be planning to go for around 120 minutes. That's 2 hours in total, with about 30 minutes each allocated to each of our speakers, and we'll be sharing a link for your attendance certificates later in the event. It'd be great if you could post on LinkedIn and tag us when you've received your attendance certificates. In terms of questions, please type those into the chat and I will mark them for each of the speakers. So we'll be doing a Q&A session after each speaker, and then we'll be moving on to the next speaker. So please do be quick with your questions. We will be having to manage time, so it may be that we don't have time for all of the questions today. In terms of our first presentation, unfortunately, Professor David Barton of the University of Leeds is unable to join us live today. However, he has provided to me his slides and a script for the presentation, and with his permission, I will be delivering that presentation in his stead. So please be aware that for any questions, I'm not going to be able to answer those as Professor Barton would. So with that, I'll go ahead and move on to his presentation, after which we will have Dr. Zabala and Dr. Llavori, then Dr. Xicola, and Dr. Diew at the final presentation slot for today. So without further ado, let's move on to David's presentation. Okay, so David is a professor of solid mechanics at the University of Leeds, and he's been researching automotive braking systems for over 30 years with 2 main areas of interest, those being understanding and mitigating the noise and vibration problems in brakes, such as squeal and judder, and secondly, investigating lightweight materials as alternatives to the heavy grey cast iron rotors currently in use on most automotive disc brakes. In terms of the agenda, we'll begin with a little bit of background for automotive friction brakes, which may not be familiar to all of you in today's audience, as I'm sure we have some specialists, but also some here for general interest. We'll then be highlighting the increasing importance of non-exhaust particulate emissions and the impending legislation to limit such emissions from friction brakes. We'll then move on to describe the work at Leeds on the reduced scale testing of brakes with a focus on emissions measurement, and after which we'll be looking at a case study on a small-scale test bench to measure how effective laser cladding of grey cast iron surfaces may be in reducing emissions. We'll then present a full-scale or a second look, at the effect of corrosion on emissions using the full-scale dynamometer, also at the University of Leeds, and finally a summary of findings and future prospects. So moving on, for those of you that may not be familiar with automotive friction brakes, on the left-hand side here we have a very traditional car disc brake featuring a grey cast iron disc and caliper containing 1 or more hydraulic pistons, which are used to press the brake pad against the rotating disc and generate the necessary frictional torque. In the right-hand image, we have a much more modern, lightweight design typically fitted to those of more upmarket cars or sports cars. It has a lightweight caliper and a 2-part disc with a light alloy hub and drilled ventilation friction ring. As you can see, those drilled holes there, and also vents that are just present at the top. but it is still made from heavy grey cast iron. In terms of the basic layout of a hydraulic disc brake, we can see on the left a section of a piston disc brake in which the action of the pistons are to push against the discs, and you can clearly see how that happens as they move towards the discs or the rotor. We then look at the friction surface much more closely. We can see a classic three-body situation with the disc shown in blue on the right-hand side there, the pad in green, and the transfer layer formed between the two in orange. It's the tribological interaction between these three bodies that creates the frictional torque required to slow the vehicle. But as we know, friction generates wear. Wear leads to particulate emissions, which is commonly known as brake dust. And there have been increasing concerns about the effect of particulate emissions from road vehicles on human health, especially in urban areas. Particulate emissions are classified by their mean aerodynamic diameter into several different ranges. Different particle sizes, when inhaled, can penetrate into different parts of the body, with submicron particles able to cross into the bloodstream and even find their way into the brain, with those indicated such as PM1 and PM2.5. PM5 will be in airways, and then PM10 will generally be captured in the actual nose and mouth itself. And with that penetration into the brain, there have been links found between nanoparticles in the brain and Alzheimer's disease. The second graph on the right indicates that as PM2.5 and PM10 emissions from internal combustion engines have diminished, largely due to the use of particulate traps on diesel engines, the contribution from so-called non-exhaust emissions will continue to rise and may already exceed that from exhaust emissions. And of those particulate emissions, we can see that nearly 1/3 of those is friction brakes. So let's now take a look at friction brakes in electric vehicles. Firstly, all types of EVs are still required to carry friction brakes for situations when regenerative braking is ineffective or inadequate. One important consideration is that EVs tend to be significantly heavier than their internal engine equivalents, as shown in the right-hand figure, where we can see vast differences in weight between the different classes of vehicle. On average, PEVs are 26% heavier than their internal combustion engine counterparts. And GVWs are typically over the 2-ton mark. Tire and road surface emissions are therefore likely to be higher for EVs, but brake emissions may also be affected with the increasing vehicle weight. The fact that friction brakes on any EV may be used less frequently due to contribution of regenerative braking may make them more prone to corrosion and to other forms of surface damage. Now, turning to limits on PM10 emissions under the Euro 7 legislation set to be introduced next year, different limits have been set for PEVs and all lightweight and medium-sized vehicles, as shown in this table. Limits are also due to be introduced for HGVs by 2030, but one important difference is that these are likely to be normalized with respect to vehicle weight or axle loading, whilst the light vehicle limits are dependent on weight. OEMs and brake system suppliers are struggling to find ways to meet these limits, and the most likely short-term solution seems to be the use of some form of hard coating or surface treatment for the standard grey cast iron rotor. Excuse me. The Euro 7 emissions to be measured to UN GTR 24 test schedule using the WLTP braking duty cycle. That is the World Light Duty Vehicle Testing Program. But this requires the use of large and expensive dynamometer test equipment, which may be beyond the reach of many brake system suppliers and manufacturers. Reduced scale testing may be able to quickly and relatively cheaply evaluate emissions prior to full-scale dyno testing. And the University of Leeds, and David Barton specifically, has developed one such test bench around the Bruker UNT Tribal Lab, which we will take a look at in the next slide. Yes. So moving in this case, as you will see it from right to left, clean air is supplied via a HEPA filter that's passed through an enclosure around the small disk sample that goes through exhaust ducting, where it's sampled through a Ducati cascade impactor. Good particle uptake and steady flow conditions are confirmed by the CFD analysis, which we have there on the right, and that has been programmed to the WLTC duty cycle, and this is in the Bruker software, and a very good correlation has been found with full-scale dyno tests when scaling effects are taken into account. The image of said scaling we can see here on the top right. Okay, the scaling approach is to replicate as much as possible the geometric and tribological contributions of a full-size disc brake. So generally, there would only be one small piece of pad material pressed into the small sample disc. The area aspect ratio, the sliding velocity ratio, and the angle subtended by the pad are all set to be in the same range as a typical passenger car brake, and the disc mass is also scaled accordingly to give the correct thermal inertia. Now we're going to move on to describe the first case study carried out using this small-scale test approach. The starting point for this case study was a full-sized CV brake disc, which had been laser clad to give a 2-layer coating consisting of roughly, 100 microns of thick, pure 430L stainless steel buffer layer, and then a composite top layer of 430L plus titanium carbide particles. The small 97 millimeter diameter samples were cut from the disc and were tested against a standard low-met friction material over 8 full WLTP cycles. Friction, wear, and emission results were compared with those for corresponding uncoated gray cast iron discs as a reference. And here you can see the pad sample that's used mounted into the Bruker rotating platform with the guard plate installed to prevent particle loss down the sides of the platform. Okay, now looking at the friction and wear results for the full 8 WLTP cycles conducted, we can see that the laser-clad rotor took more cycles to reach roughly the same coefficient of friction as the gray cast iron. So we can see there to WLTP cycle 5, the coefficient of friction cycles are very similar. And it may be that it takes longer for the laser-clad surface to establish a stable transfer layer, a fact that could be of concern for brake suppliers whose systems are expected to work perfectly from the first brake application. And perhaps because of this initially low coefficient of friction, pad wear for the laser-clad sample over the full 8 cycles is reduced, as we can see for the figure on the bottom right. But more importantly, wear of the laser-clad disc is actually reduced to that is barely detectable. Okay, now looking at emissions results as measured by the Ducati over the final 4 WLTP cycles, it can be seen that the laser-clad sample produced a lower particulate mass across the whole particle size range down to 0.6 microns. And importantly, both PM2.5 and PM10 emission masses were significantly reduced compared with the uncoated sample. All very encouraging results. So these emission results can be extrapolated into a full-size test vehicle by applying the appropriate scaling factor and assuming that the vehicle is fitted with 4 similar disc brakes. The results of this extrapolation for both standard gray cast iron and laser-clad rotors are compared with the current Euro 7 limits in the figure on the left. As you can see, the emissions for the uncoated rotor are predicted to be 4 times more than the limit for internal combustion engine vehicles. In contrast, the laser-clad rotor results are much closer to the limit, and we could now, excuse me, sorry, and we can now look further into reducing those particulate emissions with further optimization of the friction material. Of course, the set limit for EVs is lower still, and it's worth bearing in mind that the results that were generated are for as new discs and pads without any allowance for any in-use environmental factors such as corrosion. Now, in order to quantify the potential effects of corrosion on emissions, but also to consider prospects for light alloy replacement of the traditional grey cast iron rotor, a further study was carried out using the full-scale dyno at the University of Leeds. Here we can see lightweight alternatives that were considered alongside the standard grey cast iron disc brake. Firstly, a prototype aluminium metal matrix composite rotor, as previously fitted to the Lotus Elise and Chrysler Prowler. And secondly, a plain aluminium disc alloy coated with a luminous ceramic surface layer, as applied by plasma electrolytic oxidation. The two aluminium discs both used bespoke aftermarket brake pads supplied for the Lotus Elise, whereas the grey cast iron used standard low-met brake pad. The upper left photo shows the grey cast iron disc installed on the dyno, which utilizes a special squeal-reducing 4-pot caliper. The brake head is enclosed with an airtight chamber to which clean air is supplied via a HEPA filter. The air on the outlet duct is sampled at a remote location using the same Ducati impactor as for the small-scale tests. After initial drag braking tests at different pressures, corrosion for all three discs was conducted in a salt spray chamber according to ASTM B177. And we can note there that the disc brake, or the rotor, is inclined at a small vertical angle just to allow for runoff of the salt spray itself. Okay, so after bedding in, all three rotors were subjected to repeated drag braking testing at a speed of 150 RPM and hydraulic pressures of 5, 7.5, and 10 bar. Each test lasted for around 120 minutes and was repeated 3 times to check for consistency. Then, after 96 hours in the salt spray chamber, the whole sequence was repeated again for the, at that point, as corroded rotors. This slide shows the images of the rotor surface during the various stages of the complete test cycle. Looking at the grey cast iron at the top, you can see that the nice black transfer layer has formed by the end of the uncorroded tests, looking at the 10 bar labeled there. After salt bath exposure, a thick layer of red dust has formed on the grey cast iron surface. And although the corrosion products are removed during the subsequent bedding in, scars and crevices remain on the rotor surface, which may have inhibited the formation of a stable transfer layer. The mixed metal composite rotor in the center also shows salt deposits after the corrosion cycle, and again, the deposits are largely removed during the subsequent braking, but evidence of surface damage remained. Finally, the PEO-coated aluminium rotor shows very little effects of corrosion, and a transfer layer was very quickly reestablished on its rubbing surface. Looking at the sectional micrographs taken through the surfaces of the three rotors at the end of the test sequence, it's apparent that the graphite flakes near the surface of the grey cast iron rotor have been affected by corrosion exposure. You can see those pits there. The section through the mixed metal composite surface reveals that the pits have been formed by the removal of the silicon carbide particles due to corrosion effects of the aluminium matrix. In contrast, the vast majority of the PEO rotor surface remained intact, although there is some evidence of pitting and delamination at the very edges of the friction ring, where the PEO process is less effective. Okay, and finally, turning to emission results. One important point is that the Ducati measurements have been normalized with respect to the total friction work done in each test to allow for the varying coefficient of friction. The histogram plots show mean PM2.5 and PM10 emissions before and after corrosion in each case to the same scale. The substantial increase in emissions for the great cast iron rotor after corrosion is very obvious from these plots, as we can see there on the right. Emission from the mixed metal composite rotors also increased significantly after corrosion, especially at lower applied pressures. And in contrast, the emissions from the PEO rotor were consistently the lowest of all three rotors, and importantly, were not significantly affected by the corrosion cycle. And now, in summary, EVs are still going to need to carry friction brakes for the foreseeable future, and the weight of these brakes and their inherent and their infrequent use are, of course, a case of concern. Great cast iron rotors are not only heavy, but also prone to corrosion. They're unlikely to meet such Euro 7 emissions limits without the form of some kind of hard surface coating or treatment, such as carboferritic carburizing, FNC. Aluminium rotors give significant weight saving at moderate additional cost and have been shown to give good friction and thermal stability up to moderately high surface temperatures. Emissions from the PEO coated aluminium rotor were reduced, even allowing for the effects of corrosion. The Euro 7 legislation takes no account of the effects of corrosion or the large number of nanoparticles that can sometimes be emitted, which are the most dangerous from a health point of view. There is still much work in progress. So thank you all very much for sitting through my best attempt at Professor Barton's talk. As you can see there, his email is on screen. You'll also have this talk will be present in the recording. So should you have any further questions, you can email him there. Just also like to, on his behalf, acknowledge the Leeds PhD students that took part in this work, as well as the industrial companies Cummins Meritor, Curtis Wright Keranite, TMD Friction, Bruker, and TWI UK. Thank you all very much for listening. As I said, we will not be taking any questions for, if you want to ask questions, please email David. But now we will be moving over to Alaitz and Iñigo's talk. So I will invite both of them on stage.
Shall we start?
Please do, sorry. Yes, please go ahead and show your slides.
Okay, so I'm going to share the screen then.
Okay, there we go. Okay.
Please let me know if
great.
you can...
Please proceed.
Okay, thank you very much. Well, first of all, I would like to thank you to the organizers for providing us the opportunity to present here today. So today, me and my colleague, Iñigo Llavori, we're going to present the work entitled WLTP brake cycle in tribometers. This is the index that we're going to follow during the presentation. First of all, a brief introduction to put the work into a context. Afterwards, we're going to see which are the key factors for a proper implementation of the WLTP on a tribometer. And finally, my colleague Iñigo will finalize with the most relevant results, showing the correlation between the dynamometer and tribometer results and also the final conclusions. First of all, I'd like to start providing a quick overview about Mondragon University, which is a private and cooperative university belonging to Mondragon Corporation, which is a corporation that is composed by more than 260 companies. And the university represents the knowledge division in this industrial environment, although we're not exclusive. So all of the research and innovation that we perform at Mondragon University, it's mainly industry driven. And a good proof of that is that 50% of the programs are funded by private companies, and up to 70% of the doctoral theses are also funded directly by companies. We are considered to be the first university in Spain in knowledge transfer and the number 7 in Europe. The project that we're going to present today, it's a success story of this collaboratory framework between the university and EtherTech, Favor Etherland Group. And I would like to take advantage to say thank you to our PhD student, Sergio Fernandez, for all of the hard work. The motivation of the work starts with the increasing health concern related to the breakaway particle emissions to the atmosphere. The following graph shows the PM10 particle emissions of a vehicle along the time. As we can see, in the last couple of decades, the amount of exhaust emissions has decreased considerably, and nowadays, the breakaway particles represent a significant amount of the total non-exhaust vehicle emissions. In this context, for the very first time, the European Commission will launch a new regulation, the Euro 7, at which the amount of PM10 particles that could be emitted from the braking systems will be limited. It will set an initial number of 7 milligrams per kilometer at first, and later on, this value will be decreased due to the eruption of the electrical vehicles. The standard that has been adopted for the regulation for the brake emission measurement is the GTR number 24, which is based in the WLTP cycle. Considering the amount of new solutions that are being developed in order to mitigate this breakaway emission, nowadays the dynamometers are saturated, and moreover, they represent a high cost in the pre-validation stage. Accordingly, alternative tools in order to have cost-efficient and rapid material screenings are of high interest, such as tribometers. Now we're going to move on in order to see which are the key factors for the implementation of WLTP. So first of all, I would like to go through this summary of the WLTP cycle. As you can see, it's composed by a total of 303 braking events at which the distances, speeds, and decelerations are described. The regulation asks for performing 6 repetitions of this cycle, and the emissions are characterized in the repetition number 6. We can see that the time of the testing is quite high. In order to have a proper implementation, the very first step is to have a good understanding about the functional differences between the dynamometers and tribometers. The first one, it's related to the inertia. While the dynamometers, they do have a flywheel to simulate real inertia, the tribometers, they don't have any inertial mass. That's why in the tribometers, we impose the motion. So the system, it's not really braking. We are simulating the deceleration. While in the dynamometers, we do have a real braking, dissipating the kinetic energy. From the point of view of the control, dynamometers, they do have a closed loop at which the pressure is actively controlled depending on the coefficient of friction of the tribo system under test. On the other hand, in general, tribometers, they work under open loop conditions at which we need to fix the input variables before the braking events, and they are set constant during the testing. Now we're going to go through all of the different aspects that should be considered for a proper implementation, starting from the kinematic implementation. I would say that this is the easy part. Considering the WLTP, it's fixing both the deceleration and the speeds. Basically, we just need to translate this information into the rotational speeds of a tribometer. In order to do so, the variables involved are, on the one hand, related to the vehicle under study, more specifically to the vehicle wheel characteristics. And on the other hand, they are related to the tribo system configuration, more specifically to the effective radius of the tribological test that we are going to perform. Regarding the loading implementation, we know that in the dynamometer, all of the kinetic energy is dissipated due to the frictional work, by means of the frictional work. So based on that, our miniaturization is based in a functional area scaling at which we need to fulfill two equivalence criteria. On the one hand, both systems should present equal energy dissipation per unit area. In considering that the breaking distance is fixed, both systems should also have the same specific friction force. So once we apply those two criteria, if we define the area of the path that we are going to use in the tribo system, we can directly compute the normal force. However, this normal force will depend on the coefficient of friction, which is an output of the system, and it's an unknown variable at the beginning of the test. Accordingly, we need a recalibration strategy for the normal force. And here we do have a scheme showing the steps that we follow in our system. We start with an initial estimated coefficient of friction, and later on, during each of the repetitions of the WLTP cycle, we evaluate the real dissipated energy and we recalculate the normal force accordingly. And we repeat this step all over the repetitions, so that by the time that we reach the repetition number 6, at which the emissions are measured, the dissipated energy is very close to the target one. Once that we had a look about the key factors of the kinematic and loading implementation, I would like to provide an overview about which are the required tribometer specifications if we would like to reproduce the WLTP. In order to do so, we selected a large SUV vehicle as a heavy vehicle. Here we do have the rotational maximum speed required in the tribometer, depending on the effective radius selected. As we can see, if we select a small radius, as the radius is decreasing, the maximum RPMs are increasing in a non-linear way. It should be considered that many times the miniaturized samples should be extracted directly from the real disk, which means that the usable radiuses could be small, so that the maximum RPMs required could reach up to 8,000. Regarding the maximum normal force required, this will depend on the coefficient of friction of the tribo system under test. As we can see, there is a linear increase depending on the area. The differences between both coefficient of frictions tends to get bigger for bigger areas. However, considering both cases, the maximum normal force lies below 1 kilonewton. Finally, we do have the maximum torque required in the tribometer, which is independent on the coefficient of friction since it depends on the friction force. And we can see the maximum values are below 15 newtons per meter. Finally, we do have the requirement for the particle collection and characterization. And here we can see the scheme of the setup that we developed in the Bruker UMT Tribolab following the GTR 24 specifications. First of all, we do have the airflow and the air conditioning. Afterwards, we do have an anemometer in order to measure the speed of the air and to adjust it so that we can ensure isokinetic conditions. And finally, we do have 2 sensors for the emission characterization. On the one hand, we do have an optical sensor for in vivo monitoring of the emission. And on the other hand, we do have an impactor to physically collect all of the particles so that we can measure the weight later on. So now I'm going to give the floor to Iñigo so that he can continue with the presentation.
So thank you very much, Alaitz. And now we will continue with the results and the correlation analysis. Next, please. So here you can see a simulation of the breaking event, and I want to focus on the actuator or the tribolab. There you can see that we applied a normal force, and then we can monitor the brake speed, the decrease of the brake speed, the evolution of the contact force and the friction force, the evolution of the temperature, the rise of the temperature due to the energy that we introduce to the system. And finally, also we can see the particle emission that happens during the braking. Okay, this is only for one braking. And then we can analyze the braking metrics that we have in the next slide. Yes. So starting with the kinematic performance in the left-hand side, in the figure we have in the x-axis the time of the braking event, and in the y-axis the braking distance. So we can compare the target that we have with the experience that we obtain. As Alaitz said, this is the easy part, and we can check that the evolution of our experiment is quite close to the target one. Regarding the dynamic performance in the right-hand side, again, in the x-axis we have the time, and in the y-axis we have the force. Checking the contact force, we can see in the gray, we have quite stable normal force. And contrary with the friction force, we can see that we have an increase over time. And this is because we have fixed the normal force, and the friction force is the evolution of what happens during the braking. So again, we can compute the average friction force, and we can see that the target friction force is quite close, or the obtained average friction force is quite close to the target that we have. So once we have defined these values, then in the next slide, we can compute the dissipated energy, and we can see the results. Again, in the x-axis, we have the time, and the y-axis, we have the dissipated energy evolution. So here we can see that there is some discrepancies between the experiment and the target. And this is because, as I said earlier, the friction force is not constant during braking. So at the start, we have a little bit more difference, but at the end, we correct that and obtain quite close dissipated energy. So this is for one brake event. Then we can compute, next please. We can compute for the complete cycle. Here in the x-axis, we have the brake numbers, all the three brakes that we have on the WLTP. And the y-axis, we have the accumulated dissipated energy. So what we can compare what we are obtaining across the braking events. So for the first repetition, we have like 23% more dissipated energy. This is quite high, but once the algorithm that corrects the friction coefficient kicks in, next slide, please. Next, yeah. We can compare the performance on the last repetition, and the result that we obtain is quite good, around 7% difference. Usually in tribological tests, the differences around 10% are quite normal, so this lies within that value. So next, please. We can say that we have a really good correlation between the tribometer performance and the dynamometer performance in terms of accurately reproducing the kinematic, dynamic, and tribological behavior. So now the question is how the particle emissions compare, the particle emissions measured in the tribometer, how it is compared with the dyno. So we have here in the next slide. Yeah, so this correlation is for the GCI and low metallic case, the current solutions that are in the market. In the x-axis, we have the different repetition of the WLTP cycle. And the y-axis, we have the PM10 and 2.5 values that we obtain. In the first repetition, as I said before, we introduced to the system more dissipated energy. So we obtain more particle emission. Again, also we have to consider that there is a bedding process here. So essentially, in the first repetition, we have quite a large amount of particle emission. However, in the consequent repetitions, we have a really stable values, and in the sixth repetition, where the comparison, or let's say the measurement, is performed officially in the GTR, we obtain a quite similar results, less than 10% difference between these triboppers. So if we go to the literature, we can see the interlaboratory round-robin reports that says that a difference between 20% on the laboratories that comply with the GTR are quite normal. And because we obtain less than 8%, we can say that for this tribopper, we obtain a really robust comparison. But what happens with other materials also? We can see in the next slide, please. Again, this is the cast iron that we compare, and then we can see different solutions. Those different solutions have different particle emissions, so we can see that in all cases, the correlation is quite good. The worst that we have is around 20% with this, which is within the typical difference that we can see in the literature. So we can say that we obtain a really good correlation in the tribometer comparing to the dynamometer with different solutions. So now, just to finish my talk, we can draw some conclusions. And yeah, we saw an overview of the challenges of the implementation of the WLTP standard. The dissipation energy that we introduce is quite important. So we developed the complete W cycle in the tribometers in terms of the dynamic, kinematic, and dissipated energy, and we obtained really good results. We can say that the PM10 emission has been successfully replicated in the tribometer compared to the dynamometer results. And therefore, we can say that when key physical parameters align, the tribometer should reliably replicate the dynamometer conditions for PM10 emission, at least for the WLTP standard. Obviously, because we are talking about tribometers, further improvements can be made to optimize the duration of the test, because as Alaitz said, the complete WLTP test is 30 hours. So that's too much. And in terms of looking for a screening process and a screening tool, we are developing an optimized version of this to have like a quite fast comparison. So that's all for our part. Thank you very much. And now, if you have any questions, we can answer.
Well, thank you both very much for that fantastic talk. My apologies for the when I was introduced, I really needed to cough and I didn't want to do it on microphone, so I'm sorry about the delay. We're saying please begin. To everyone in the audience, please type the questions you have into the chat and we'll do some Q&A. I think with my for the speed at which I went through Professor Barton's presentation, we are a little bit up on time, which is good. We do have one question from Mukesh, which I think would be good to answer here, and then we can see if there are any other additional questions specifically on your presentation. So Mukesh asks, "Hi everyone, thanks for the nice presentation. I presume they mean here, what rubbing temperature of the interface would you expect in a PAV during friction breaking? So the majority of the breaking will be through regenerative. The ideas of what temperature the motors may reach."
Yeah, do you want or?
Yeah, I can answer. So essentially, essentially we need to consider the conditions for this particular tribopper. We need to perform the calculation in order to how much energy dissipation should be applied in the tribometer. Once we have that, then obviously the materials, even though the materials are the same, their geometries are different. Okay, so the comparison between the temperature might be different. The dynamic that we will obtain between the tribometer and the dynamometer will be almost the same, but the values will change a little bit. And also, one thing to consider is that usually the thermocouple that it is used in the dynamometer are usually touching the surface of the brake disc, but not in the contacting surfaces. Okay, because the materials are quite different. They will have different temperatures, the discs and the pad. So it is really, really difficult to estimate the temperature, if not impossible, the real temperature at the surface. We have analytical solutions to have the temperature of the pad. Okay. But obviously that's a really difficult thing to validate. But yeah, we have good correlation with the thermocouples that we have. I'm not quite sure how much will be the temperature in the electric vehicle. I will guess that it will be lower than the solutions that we have right now, because because the braking process is not only done by the brake pads and the discs. So I don't know if that answered the question. I don't know if Alaitz, you want to add something?
Yeah, just a couple of things. Well, we didn't went into a lot of details due to the time limitation. Temperature is one interesting part of the miniaturization. In this sense, I would say that the fact that the WLTP cycle is quite mild makes that even if we don't reproduce the temperatures perfectly due to the miniaturization, the reached temperature, it's below the one that changes the emission behavior. So that's why we do have a very good correlation. I agree with Iñigo that when we go to electric vehicles, on the one hand, we do have the fact that they present bigger mass, so that you have more kinetics to dissipate, but you do have the regenerative as well. So probably, the forces will be lower, the generated temperatures will be lower. So we're in a safe place to maintain the good correlations that we do have.
Okay, thank you both very much. It's a very comprehensive answer. I think that's I would say that's certainly answered everything that Mukesh was asking. We have another question here from Vincent, who asks, or who says, excuse me, thanks for this nice presentation. When you change contact size from real brakes to tribometer scale, you take into account the apparent contact area. What about the real contact area and consequently local contact pressures? In other words, how do you take into account the roughness of the sample? Well, this is always a nice complicated one.
Okay.
I think that's for you, Alaitz.
Okay. Okay. Yeah, it's true that apparent contact area is not equal to the real one. This is completely true. In that case, I need to say that we do put a lot of effort on the proper alignment, and we verify that the contact is good, but still the roughness is not involved. In that case, that we are testing braking systems on the part material generates a tribal layer in the disc. Going with the apparent contact area, it's quite safe in comparison to other systems. So the answer is we go with the apparent one. And I think that considering the nature of this tribal system, it's quite a safe place. I would say that if we change quite a lot the roughness of the disc, rather than changing the contact area, probably you could change the mechanism by which the wear mechanism, so it could have effect on the particle sizes and how they are detached from the surface. And this is a research line that we do have open. Well, we hopefully will go through it in the future months if everything goes as expected. Yeah.
I would add something, because it is flat-to-flat contact. There is a certain, geometrical area that will be representative of the total contact area, and I think we are within that representative area. And another point is that when we cut samples from the pads, we maintain, the original surface area untouched, so that when the discs touches the pad, it is, representative as close as possible to the real parts.
Yeah.
Obviously, because the size, we will have edge contact effects, but everything is not perfect. So,
Okay. No, thank you both very much. Yeah, it'd be very, excuse me, sorry, be very interesting to see further work on roughness. It's depending on the length scale of your tribology, can be very interesting indeed.
Sure.
We have a final question. I think if we do final question for you both, hear from Fabian and then move on to Agusti's presentation from there. So thank you for the question, Fabian. He says, thank you for the presentation. Have you tried using the friction force as the control parameter on the tribometer? Were the emission results from the tribometer scaled in any way to match with the emission results from the dyno?
Yes.
What do you want?
We have tried. This is a work in progress, obviously. But I have to say that I think from our point of view, the key parameter of reproducing as close as possible the same results in the dyno is the dissipated energy. Okay, when you are controlling instead of a normal force, let's say the friction force, the loop that you need to have for the correction, it is not fast enough yet. So it means that the correction is slow, and because of the dynamics of the tribometer, and you have to be fast. That's the main thing that you have to be. You have to be fast, and if the system is not fast enough, you will dissipate more energy that you want. So at the end of the day, yes, you can use it, but at least from our point of view, we are working on it, obviously. But there are a lot of work to do to ensure that the dissipation of the energy of each break is really well controlled.
Yeah. I would say that at the end of the day, it's quite related to the dynamic response of your tribometer, how it performs. So depending on the speeds that you do have, you can have one or other approach. So in our case, the one that was best fitting was the normal force control. Yeah.
Okay, thank you both very much. So I think with that, we'll say thank you and move on to our next speaker, Agusti Sin.
Thank you very much.
Thank you.
Okay, thank you.
Okay. There we go. So thank you very much, Mohamadou. Dr. Mohamadou Diew is a tribology applications scientist at Bruker Nanoservices and Metrology with over 19 years of experience He specializes in tribology, contact mechanics, materials, coatings, and wear. He completed his PhD at École Centrale de Lyon, focusing on friction modifiers and lubrication regimes. Dr. Diew works on various tribology applications for industries and for academics. I'd also like to take this opportunity to thank Bruker as our partner for today's webinar. And with that, I'll hand the stage over to you, Mo.
Yeah, thanks, Sam. Thanks everyone for joining for this Mini-Symposium webinar. I think that the previous talk already show a lot of, I say, inside view of the braking and the potential, I say, impacts of the EV. I will come a little bit on it in the introduction and show you a little bit some tools that can be used, and some of them are already presented here for characterizing brake materials for different type of applications. In this talk, I will first start with a game changer, talk about EV impact on braking, before going to explain a little bit, to say, the criteria or the parameter that can define, that can be used, I say, to define the right brake materials. I think that all of them, some of them already, I say, highlighted here in the previous talk, and show a little bit one way of setting, I say, a tribo testing using a tribological approach for brake application, and at the end showing some braking tools proposed by Bruker. The game changers are already, you can already remember on the first talk from even David or Mondragon University with Iñigo and Alaitz, or Agusti. You see that the game changer will stay the same. Like we want to move for something that becomes cleaner for the environmental, I say, purposes. And at the end, we want all the industry start developing new systems with less time, really faster, and want to do it at low cost. It means at the end, we need to develop something faster and cheaper. And for this one, we have, I say, more and more electrical vehicles. And this one also, even with classical engines, we have, I say, the good health and well-being that stay also a problem. And we can see also all things that already presented by Agusti and David Barton concerning the Euro 7, I say, requirements, where we need to have, I say, less particles, and these particles to be sure that we will help, I say, to increase or to improve, I say, the good health, even with, I say, car on our roads. These regulations are, I say, more severe in Europe, in US, but Asia is coming also in the same mood to increase, I say, the severity of these regulation. Currently, when you have a look on closer, like what already, I say, presented by David concerning, for example, the EV impacts on the braking. On the EV car, you have, I say, mainly the battery charge that I use to move the car. And during braking, we have one part of this energy that is generally, I say, for the classical engine, ECE engine, lost by heating, for example. We try to recover this part of this braking, and the last, I say, part to stop the car need to be done by the friction materials. In this case, we will use, I say, less the friction materials or the braking up systems compared to ECE car, I say, the classical car that we know. And we will face, I say, we need to face all of these problems, like, for example, having corrosion on the unused brake components, and to be sure that during emergency, when we brake at high temperature or high speed, the car need to stop. And in this case, we will face, I say, the brake need to be good, I say, at the time that we are requested in. This thing will have an effect. Also, I say, the increase, as I already said, increasing of the importance of emergency and low speed braking. But in same time, we will have, I say, all problem linked to emissions. We will have, of course, less volume of wear particles, but probably finer particles due to the oxidation that happens on the surface. The tribal challenges will be more to develop new materials that can resist for this corrosion on long idle periods, and fading that can support high temperature applications, for example, for emergency stop. thinking about running on a highway with an electrical vehicle and you brake, you will have a heavy vehicle that you need to stop in few times. And the other thing is more time to time for cities. And you, as you know, the electrical vehicle is quite cars, really no noise, less noise, and the braking will be one, I say, one area where we will continue to generate noise due to braking, and this thing will be probably a thing that more and more industries, even customers, having a look on this. How to find the right braking? We see that with this previous, as I talked, many parameters have an effect on the brake material that we need to choose. You have also the braking performance with friction, wear, and particle emissions. You have the fading, resistant at high temperature, getting low noise, low vibrations, good wear resistant, less heat dissipations, because mainly when you brake, you will generate heat. And how with this say regenerating with e-vehicles, probably one part of this is recovered, but not all. We will continue to generate this heat and all the environmental consideration. But at the end, we will need, I say, something that stop the car. It means we will have frictions that could be around 0.4, 0.6, depending on the type of material that we are thinking. And but this work, I left it to brake part manufacturer to develop the right tool for this. Currently, to characterize the right braking, as you already see on the presentation of Agusti and Iñigo and Alaitz, they show that mainly, the best, I say, testing will be for us, for all of us, I say, the real vehicle. But this test is realistic, in a realistic condition, in terms of road, in terms of environment, in terms of everything that we can think that are completely different to the standard. But this type of test is, I say, expensive, complex, and at the end it's really time consuming, and we need, I say, to collect a huge number of information, and at the end we need to find the right way to explain it. It will be a little bit complicated. That's why more industries moved to laboratory testing in a standardized protocol like the AK master and others. And this kind of testing will help, I say, to define and do the screening of material. But when you have a look, when you take a full dyno, you need a full rotor, a full brake disc with a caliper, with all other things. As Agusti said, the caliper will have an effect. The grease that you use on the backside of the caliper will have also an effect. The roughness of the surface, we already talked about it, will have probably an effect. And you have also two materials, one that are the composite materials from the pad materials, that this material can be, I say, sometimes electrical insulated, that can create, I say, some charge in some electric charge in the contact due to this, I say, braking event or friction events. And this thing can start, I say, some micro pitting or others on a material. And this, all of this thing is many parameters that can affect in same time the contact. At the end, you have a complex testing where you will put a lot of money. It will take a long time to be run, and at the end you will, I say, really did not really know what is the impact of each factor on your system, or you need to put a huge amount of money. In between, you have scale dynos, the way you can have, I say, small bench tests is where you can put also a complete rotor on some piece of that. And you have, I say, another possibility is more using model tester. It more moving to something that will be more, I say, industrial level or academic level with, I say, a simple pin on disk testing or 3 pin on disk testing, where you can have the possibility to know exactly, to control all the parameter and know the pressure that you apply, the speed that you apply, the temperature, the environment, and characterize well what is, I say, the impact of each of these parameters on the system. But if you want to go now on this model tester to describe something, we need, I say, to start with a tribal system. What is a tribal system? It can be defined, I say, with 6K elements, like the contact geometry, the type of motion, the operating condition, load, speed, frequency, duration, and others, the material properties and chemistry, the surface topography that are not that can be important in some case in the environment. And when we define this tribal material, this tribal system, we can also, I say, define which type of equipment do we need and surface analysis that we need to get, I say, to study this type of system and get the right outputs that we are expecting. But keep in mind that tribology is a multi-scale and multidisciplinary science. we need to take into account different things that sometimes will not be so trivial. The tribal approach that I present here is more taking, for example, the brake conditions with well-known SI parameter, vehicle parameter, weight, inertia, all thing, rotor diameter, tire diameter, to get SI to the parameters that we can convert to tribal system parameter, to our tribometer parameter. At the end, you will have SI the braking conditions. Is it something that looks like more the AK Master, where we are driving, I say, high-speed car or something like that, or something that will be more city application. And for this, we can use, I say, the guideline designed by the standards. Friction materials, really important, because it's a part that we will need to use to characterize the friction. Design will have an impact. If we here, for example, we see a plain disc rotor without any holes, but if we have holes, potentially these holes can be also generating all the wear mechanism on the system itself. The environment, do we have humidity that can create corrosion or others? And this thing can have also an effect also on the friction behavior and particle emissions. If we convert this vehicle parameter to tribal system parameter that can be used, I say, to define a testing, we can use, I say, a flat on disk. It can be 1 pin on disk or 3 pin on disk. Both solution can work. Motion can be rotation like the rotor disk. Two component of materials using the pad and the rotor disk. As Agusti said, you can take one, say, rotor, pick on it several disks to run, I say, the same testing. Define the operating conditions through following standards or, I say, homemade protocols to only characterize different materials that we can link to the performance of a dyno, or of our material on dyno or other type of system testing. The environment, take into account the temperature, the humidity, presence of fluids or rest or dust, because currently we are only talking about braking, mainly on, I say, non-humid area. But if it rain, we will have probably water on the brake disc, and this thing probably can have also an effect on the braking events. The surface topography and coatings, and at the end, the purpose is more to go from the bigger, I say, rotor with big parts to something that would be simple button pins and a small disc. And with this, we can characterize the friction performance, the wear using surface topography analysis of the surface before and after, and also on a pin. And this thing, the size of the samples will allow us to do characterizations that can be chemical characterization to get access to the chemistry or structure modification due to the friction, and probably the generate, I say, some other characterization if you go for nano indentation, for example, to get access to parameters that change on the surface and can explain why this stability or instability on the friction behavior of the system. We add also on our system some particle emission with a filter using a Decati impactor, and this one will allow, as I say, to collect particles at different size from PM10 to PM1. Oh, using this value, we can have, I say, a comparative correlation, as we already see previously, with a dyno to build a fast and simplified method for screening friction materials at the end. And for this purpose, Bruker is proposing a multi-scale approach, I say, and tribal testers that allows, I say, to run this type of different testing and all of these tools are complementary. They help only to bridge the gap between the ideation to the industrial tribometer. And let's think that here it's the dynamometer that start here and move to the real conditions. And on this, you have, I say, tribometers that would be, I say, the focus parameter, that the focus system that we need to use for the characterization of the testing. But before this, you have, I say, optical profile meter to characterize the roughness and of surfaces before and after the testing to be sure that what really happens and how we can describe, I say, the wear mechanisms that happens in this configuration of testing that we run. You can also go, I say, if you want to go to the lower level, for example, for AFM, for example, if you see on the secondary plateau some generation of powders to characterize these powders and to know better what's really happening and what is their structure and if they can help to build, I say, a phenomenon of what really happening in the contact and that generates this phenomenon, these particles. or you have the tribal indenters that allows to characterize also the primary or secondary plateau to get either the mechanical properties and see what is the effect of this property on at the end on the overall, I say, performance of the braking system. Let's focus now on tribal applications with the TriboLab series. On TriboLab series, we have 3 different types of TriboLab systems. The UMT that is the most versatile one and allows to run different type of testing on tribology, even mechanical testing. And the TriboLab HD more dedicated for friction materials, where you have the possibility to rotate up to 3000 RPM with a torque that can be 50 Newton meter, 55 Newton meter, even at 3000 RPM. It means high torque, and you can have, I say, high power on the system. And the last one will not really, I say, focus for brake application, but more for semiconductor for polishing wafers. If I focus a little bit on a TriboLab UMT, the most versatile one, it's a system that allows, I say, to have different type of motion with 4 different type of drive that can be, I say, rotary drive, a block and ring that have a rotation also, and 2 linear movement with a reciprocating and a linear one for characterizing coatings. For example, to run scratch testing, the linear drive can allow, I say, to perform scratch testing. And all of these drive can be added, I say, on a platform, on this UMT TriboLab platform. And within a minute, we can add, I say, some environmental chambers, even controlling humidity, heating, or liquid container, or even work without any environmental control. If you use this tribometer, only taking some few steps sequence on the AK master, for example, the SAE G2522, we can, I say, run these 4 steps, and we limit ourselves to these 4 steps because only we are using, I say, a 3-pin and a 1-pin configuration. And due only to the limitation of torque of the system, we limit ourselves to the first, I say, steps and compare with different solutions. Sometimes it's enough, depending on your applications, to get, I say, the comparison of different solutions. Because at the end, as already said, Agusti, and as we already claim, the tribometers is not here to replace the dyno. It's only here to help to do a screening of materials and go furthermore if you want with a dyno. This work is done with, I say, with collaboration with Oerlikon Metco, where we run, I say, we take a TriboLab, we add a sliding thermocouple on the side of the 1-pin, for example, configuration 1-pin, and underneath we have a cast iron disc, and we run, I say, several testing, as I showed previously. It's a green mu, a burnish, a first characteristic, and a speed pressure. It means from 10 to 8 bars. And when we run this testing, we run it at 2 configurations, one with 1-pin, one with 3-pin, and compare the result with the dyno results in blue. As you see here on the underneath, we have 3-pin in contact with also the sliding thermocouple that do the measurement of the temperature. This one will show us, I say, the evolution of the temperature during the test. But if you see, I say, with a range of, with the error, I say, or the deviation of something like 10% on each of these testing, you can see that the blue line here on the friction is in the same range for the dyno, the test with 1-pin, the test with 3-pin on the same range. And this thing will be the same even on the burnish, on the characteristic value and the speed pressure. You will find exactly the same tendency. In terms of temperature, the increasing the energy for the energy dissipation through the area, I say, is similar. But when you increase the number of parts, you increase the surface. At the end, you will see, I say, more heating compared to the 1-pin, where the heating will be quite low. If you see, for example, the 3-pin is a test in the magenta. And this one, you see that the color, this one compared to the dyno, we are closer compared to the 2 others where we are so far due to the heating that will be really less because we only have 1-pin. We can only try to find a way, I say, to bypass this by only increasing the time of braking. And in this case, probably the test will be not the same like what we try to compare. What we can summarize with this TriboLab UMT, we have a system that can go up to 2 kilonewton, 5,000 RPM in terms of rotation, and with a maximum peak torque of 10 Newton meter. On this system, we can control also the temperature, the humidity, and have also the possibility to add voltage that can be AC or DC voltage in a contact for even mainly used, I say, for lubricant application, but more and more we will see because we have, I say, one composite material versus steel, and the composite material will not be can be, I say, insulating sometimes or creating electrostatic charge, and this thing can also create some other damages that we probably might have in the future and need to be investigated. And using this system, you have the possibility to screen different type of material, get the tribal performance, surface topographic evolutions, and try starting, I say, building some wear mechanism that allows, I say, to understand better how the how the brake materials behave in certain condition using, I say, simplified testing. We have the bigger one that is the Tribolab HD. And for this one, it's the only thing that you need to keep in mind that the Tribolab HD is 5 times, I say, have the possibility to get 5 times in terms of torque. 10 maximum, it can go up to 50 Newton meter at 3000 RPM. And you have the possibility to use bigger samples. It means you will generate more heat in contact. And this system is with the embedded, I say, heating the rotor disc. It means you can heat underneath the disc and get faster to 550. It will allow, I say, to compensate if you did not get to the right temperature only by friction, to increase a little bit the temperature to get to the fading mode where the temperature can be higher. And on this, you can add, I say, the particle collection systems with a with the impactor and a pump that allows, I say, to collect particles and do analyze post-mortem after the test to get, I say, how the size, the distribution, and probably some information on the if you do mechanical, I say, chemical analysis to get on the particle structure and chemistry. I already go on it. You have, I say, different point, high speed, high torque, integrated heating on the rotary disc, a self-leveling holder. It will be the same even on the Tribolab UMT. This one will allow only to be sure that on Tribo mainly, if you have two surface flat on flat, to be sure that the two flat are in contact perfectly, are conformable contact. It would be sometimes better to have, I say, this self-leveling to allow to compensate these, I say, tilt that can be happening on surface because any surface is perfect. And you can, I say, easily characterize your system with small samples. And here you can go up to 100 millimeter in terms of size of rotor disc, and coupons can 3 coupons up to 380 square millimeter. Two configuration can be possible: 3 pin on disk or 1 pin on disk, depending on what you're expecting to run. 3 pin more stable, 1 pin also something that would be simple testing, but allows, I say, both can be run. The only, I say, influence that we see currently is when you run 3 pin, you will really get, I say, heating of the system due to the surface increasing, and you will get, I say, 3 times the load that you get here. And when you only run 1 pin, the temperature will be lower, really lower. Yes, this thing already. And on the test, after the test, you will get on one plot all the parameters that you can, I say, control on the system. It means the speed, the load that you apply. You can also do the measurement of the temperature of the pad. It means on the backside of the pad, even the pad can be sometimes insulated material because it's a composite. The rotor disc with a sliding thermocouple, and you can also measure the torque that you get at the system. It means during the braking event, you can get, I say, all of this information. And using this information, we can build, I say, taking, for example, a complete AK master, building some AK master plot, say, where you can have, I say, all the different steps with even the fading or the recovery. You can also run all of this testing with even with the temperature purposes. At the end, we can obtain this type of curve when you compare, I say, the results that we get from the dyno and the results that we can get from the Tribolab HD, as already previously shown on the Tribolab UMT, where we see some correlation on the data. Even this kind of thing can also be observed. Now, the question is there any correlation? Because at the end, the correlation will depend more on the customer or the user of the system that can say, okay, these 10% or 20% in this area will be significant or not significant, or can be, I say, enough to do ranking of different material. Other again, our tools, these trimeters is not replacing a dyno. It's only here to do help for screening huge number of material and innovate faster before going to spend a lot of time and money on a dyno. Characterization of the material before testing, and even on the disk and the pad itself, and after, with I say the formation of different areas where we see that some areas where we have some polishing surfaces, some tear materials around, and even on the disk area where probably this one is a cast iron, where we have, I say, a transfer layer coming from the brake pad. If we go to more to do, I say, more analysis, we need more to go on, I say, doing chemical analysis to see better which type of structure we transfer on the surface and which type of third layers we have formed, and what is the impact on the roughness of the surface after this running in. Adding a particle collection system, as I said on the starting, we add on a chamber tubing with the impactor here. We can collect particles within, I say, different type of filters, the 1 micron, 5 micron, and more than 10 micron. And we have the possibility, I say, to characterize each of them for 3 different type of testing. For example, we can get a certain number of testing and compare these different size of particle. And using, I say, the ECM, we can also get, I say, the distribution, try to do distribution with a statistical approach and on this, or analysis on, or do chemical analysis, I say, on it to get, I say, the chemistry in of each of these material. As I proposed during on this is more to say, how can we use Tribo to build, I say, a multi-scale approach? And I think that even for something that will be well known for all the type of Tribo, I say, project or studies, but for breaking more and more, we need, I say, to go on this, like building a kind of approach where we take into account the chemistry at the early stage, the surface topography, the testing using, I say, simple test methods to get also, I say, a kind of, can be a kind of reciprocal, can be, I say, a testing that we need, I say, to have a look on the surface after test and probably improve it before going to run another test, or all the things again on it before going to move on expensive and complex testing on the dyno or the engine itself. And this thing is one type of approach, as already shown by Agusti on his presentation. You can also feel this type of approach. That means that these tribometers and all other techniques that already use, I say, well-known on tribological approach, can be also used for brake application to be better, I say, do the screening on different materials and get access to the performance of these brake systems. In conclusion, we can say that the Tribolab is an effective scale-down approach to quantify tribological properties of various brake materials, and using, I say, parameters that we can control, even the pressure, the velocity, the torque, and other systems. And this system is cost and time effective, because compared to the dyno, where and when you remember on the presentation of David, it's a good dyno for WLTP will cost something like $1 million. And here we have something that will be probably cheaper than this. And you have the thing that allows you, I say, to run several testing within a weekend that you cannot really do on a dyno. You can only have 1 or 2 run. As Agusti said, you can have more than 7 run in the week only using this Tribolab. You have the possibility, I say, to improve your system, your material, and adjusting the process, because the system in terms of scripting is quite open and allows, I say, to build even customized scripting that allows you, I say, to get access to this information and to build something that will be more, I say, robust and confident with what you are looking for. You can also replicate some regenerating strategy depending on what you really want to run. And simplified WLTP testing running on the dyno can be, as I also run on it with the particle emission collections. Thanks again. I only want to show different tools with, I say, different size of load and length scale. And I only told you, keep fun and be crazy. Stay innovative. Thank you.
Thank you very much, Mo. That's a great summary of Bruker's application options and all the possibilities that you can do with your equipment. So with that, we are pretty much at time for the event today. But I just want to stay on for a couple more minutes to check that, for anyone that has any questions for you. Additionally, for anyone that wants the attendance certificate, that is now available. Please do click on the link that is on screen right now. You will only be able to get the attendance certificate via that link. It's not going to be immediately disabled, but I would do that. Click on it, open it in a new tab, download it before the end of the day. Okay. Does anyone have any questions? Okay, so what I'm going to do is let me leave the certificate link there. And I think with the lack of questions, we shall move to bring this event to a close. So I just want to say thank you very much to all of our speakers today. Fantastic presentations. I'm sorry that Professor Barton could not be with us today, and I hope at least that my attempt at his presentation did, give you some impression about what he was going to talk about. So, apologies for that. He would, he would have been able to present it better than I did, but nonetheless, we proceeded. Thank you very much to the partner for today's event, Bruker. We at Surface Ventures would not be able to do what we do without our partners. So just want to say thank you very much to them. Our next mini-symposium will be on the 31st of July. So please do register for that. The link is in the chat now. I'm keeping the attendance certificate open should anyone else want to download that at the moment. Please do look at, do visit our website, surfaceventures.org, to see the other things that we do. You can visit recordings you can view recordings for our previous events, find links to our various social media pages, look at our LinkedIn page where you will find our newsletter, Modern Surface. And finally, I'd just like to say, if you found this event useful, please do take the time to advertise this to your colleagues and anyone else you may think would be interested. It'd be great for us to keep growing our audience and finding more that are interested in the fields of material science, tribology, and surface engineering. So with that, everyone, thank you all very much for today, and hope to see you in the next event. Goodbye, everyone.